Morning students, we are going to discuss about the topic in the course CS 8603 distributed system, and I am Meenakshi, Assistant Professor Computer Science, working in Rohini College of Engineering and Technology. Today's topic is Maekawa's algorithm. Already we have discussed about Lamport algorithm, Rickard-Agarwala algorithm. The third algorithm is Maekawa's voting algorithm. The learning objectives of this video presentation are developing an algorithm for distributed mutual exclusion, and we have to know about the advantages, disadvantages and the performance of Maekawa's algorithm when compared with the other algorithms. What is Maekawa's algorithm? Already we have discussed about two approaches, token based approach and the permission based approach. So what is token based approach? If the site wants to enter into the critical section, it requires a unique token. What is permission based algorithm? If the site wants to enter the critical section, it needs to get a permission from all the other sites. Maekawa's voting algorithm is a quorum based approach. It is used to ensure the mutual exclusion in distributed system. We know that the example for permission based algorithm is Lamport algorithm, and the other one token based algorithm is Suzuki-Kasami broadcast algorithm. Here the quorum based approach, the example algorithm is Maekawa's voting algorithm. In permission based algorithm, we have to get the permission from all the remaining sites in the distributed system, whereas in quorum based approach, we don't need to get permission from all the sites. We form a subset of sites. That subset of sites is called as a quorum, and from this subset we have to get the permission. So that is the difference between permission based algorithm and Lamport algorithm. So once again I am telling, in permission based algorithm like Lamport algorithm, Rickard-Agarwala algorithm, if the site wants to enter into the critical section, it has to get permission from every other site. Whereas in quorum based approach, example Maekawa's voting algorithm, if the site wants to enter into the critical section, it won't get permission from all the other sites, but anyway it has to get the permission from only the subset of sites. That subset of sites is called as a quorum. So here also, to implement the algorithm, we need three messages: request, reply, release. So if the site wants to enter the critical section, it has to send a request message to all the other sites in its request set. So what is the other name of request set? It is quorum. Okay. So the site send a reply message to the requesting site to give its permission to enter the critical section. After executing the critical section, a site send a release message to all the other sites in its request set. Okay, we don't need to send release for all the sites in a distributed system. Just we need to send a release message to the sites in request set. That is the difference. So once again, we have three steps to implement Maekawa's voting algorithm: requesting the critical section, executing the critical section, and releasing the critical section. So they are the conditions for Maekawa's algorithm: M1, M2, M3 and M4. Okay. So that is for every I and for every j, and I should be greater than or equal to 1 and j should be less than or equal to n. Ri intersection Rj should not be equal to the empty set. Okay, it should not be pi, the empty set. And I can ranges from 1 to n, that is the Si should be in Ri. And the third condition is again for all I, I can be in the range 1 to n. Cardinality of Ri is equal to k. So k is some number. And the condition M4 is any site Sj is contained in k number of Ris. Okay. It can participate in multiple request sets. That's the meaning. So to enter the critical section, if the site Si wants to enter the critical section, as I told, it has to send the request message to all the other sites in the request set Ri. When some other site, let it be Sj, receives the request message from Si, it has to send a reply message. Okay. If it has not sent a reply message to the site from the time it received the last release message, that is, the condition for sending the reply message is the site should not send any reply message. If the site has not sent a reply message to the site from the time it received the last release message, anyway, from one site it receives the last release message. Okay. So after that last release message is received from some other site, okay, if it has not sent any reply message to some other process, then it can send a reply to Si. That is, we can vote anyone. We cannot vote more than one. That is the meaning. Okay. So if it is already voted, it queues up the request. It has to wait. To execute the critical section, Si must receive the reply message from all the sites in the request set Ri. After executing the critical section, Si can exit the critical section. It has to send a release message to all the other sites in the request set. So the other site, let it be Sj, receives the release message from the site Si. So what it is doing means, it checks it's in its queue, is any other process waiting. So if it is waiting, if any pending requests are there, it sends a reply. After sending the reply, that entry is deleted from the queue. If in the case the queue is empty, then Sj must update its status to show that it has not voted. That is, it has not sent any reply since the receipt of the last release message. Okay. So they are the steps we need to do for exiting the critical section. So the message complexity of this algorithm is 3 into root n. So that is, we require root n request messages, root n reply messages, and root n release messages. The drawback of Maekawa's algorithm is we have a possibility for a deadlock. Okay. So that is the problem of Maekawa's algorithm. And here the critical section requests are not ordered by the timestamp. The performance of this algorithm is the synchronization delay is equal to twice the message propagation delay. Note down the difference between the other algorithms and this one. The synchronization delay is equal to twice the message propagation delay, and it requires 3 into root n messages per critical section execution. With this, we are concluding the topic Maekawa sorting algorithm. Thank you.